The brightest thing in our sky is also the easiest place for a mystery to hide. Professionals say stare too close and you go blind. An amateur says try me and points a telescope into the glare. He sees a shape that should not exist near the surface of a star. Not fuzzy, not random, a triangle. Meanwhile, an interstellar visitor called 3i Atlas is skimming the sun, and soon we all go blind during solar conjunction. Could this be a camera trick or a technological silhouette? Hit like, subscribe, and stay alert, because the clock is running. Here is the paradox. The sun is so bright that most high-end instruments are designed to avoid it, yet that same brightness can mask something extraordinary right in front of us. A backyard astronomer named Tiago streams his attempts to look anyway. From his patio, he tracks a fast mover from beyond our system called 3i Atlas as it dives toward the sun's blazing face. He fights glare and heat and turbulence and records a shifting blur. Then a viewer named Chris tries a different method and sends an image during a live show. A dark triangle sits beside a sunspot with edges that look engineered, not organic. The chat explodes. Tiago stares and concedes the moment. Chris wins the night. So what if it is not a camera trick? Could a small probe ride along with an interstellar visitor, peel off near the sun, and sip energy before the long flight out? Or are we seeing a classic case of the human brain drawing lines where none exist? We do not get months to ponder it. When an object ventures too close to the sun, as seen from Earth, the glare overwhelms our optics. That period is called solar conjunction, and it turns the world blind for days or weeks. If the triangle can be replicated, it has to happen before the window slams shut. Let us keep our footing. 3i Atlas is real. Survey telescopes flagged it as a hyperbolic intruder, which means it is not bound to our star. It has a coma, a tail, and bursts of coma. Brightness that look comet-like, with some quirks that keep everyone watching. In the cautious view, this is nature being interesting. In the speculative view, it is a vehicle making a deliberate pit stop. Both cannot be right. The only way out is evidence that survives hard questions. Here is what makes Chris different. He did not use a prominent telescope that isolates a thin slice of the sun's atmosphere. He used a refractor with a Herschel wedge that tames the blaze so you can image the sunspot crust with high contrast. Different layers, different risks, different artifacts. That choice may turn mush into pattern, or it may turn glare into ghosts. That is why raw files, multiple frames, and independent replication are the currency that matters. If it is real, it should reappear under careful hands. If it is not, it should vanish the instant we test for it. Meanwhile, the silence of big institutions becomes a character of its own. The National Aeronautics and Space Administration is not a monolith. Sometimes the pipeline from sensor to public page is slow for very boring reasons. Calibration, safety, scheduling. To an excited community staring at a countdown, that delay can feel like a cover story. To a mission team staring at limits that could burn a camera, that delay is restraint. Which interpretation you choose changes how that triangle looks in your mind. So we're going to walk straight down the middle. We will lay out the rules of a clean test in plain speech. We will show how optics can cut both ways. We will use public data where we can and invite professionals to weigh in where they should. And we will keep the energy high, because you deserve a story that moves as fast as the object itself. Your role is simple. Stay to the end, share this episode with the person in your life who cannot resist a cosmic puzzle, and keep your notifications on. The next image could tip the balance either way. Start with a patio, a sky, and a stubborn idea. Tiago is not an institution. He is a person with a modest telescope, a streaming rig, and the unsettling hunch that the brightest place in the sky is exactly where the story is hiding. He calls his channel Dobsonian Power, but the specific tube matters less than the mindset. Point at the Sunday, do it safely, try anyway. On camera, he does what most of us only talk about. He dials exposure down, threads in narrow filters, steadies his mount, and fights a river of boiling air between him and the star that keeps us alive. He begins with a prominence telescope. That tool isolates hydrogen alpha light and reveals the sun's atmosphere, where loops and tongues of plasma rise above the limb. It is perfect for fireworks at the edge. It is not perfect for crisp detail on the visible surface. Tiago knows that. Still, he tries to watch the region near where 3i Atlas should pass. His stream shows the realities of solar work. Wind gusts the scope. Heat shimmer eats the fine detail. He captures frames, stacks them, and then stares at what looks like a smudge that moves just enough to taunt him. He does not declare victory. He says it is there, or something is there, but he cannot claim what it is. He shows the blur and calls it a miss. Honesty lands harder than hype. The chat is supportive and merciless in equal measure. Try again. Different filter, different gain, different cadence. He nods and keeps recording. The clock does not care. Each day pushes 3i Atlas deeper into the zone, where glare will drown everything. So what can a careful amateur do that does not cross the line into reckless? Start with safety. The sun is not a place for improvisation. You need front-mounted film or glass filters, or a specialized wedge that dumps heat out of the beam. You test in shade. You cap the scope when you step away. You aim slowly. You never look through unknown glass. Tiago repeats these reminders out loud as he works because many viewers are first-timers, and curiosity without caution becomes damage. He is performing a story and a safety briefing at the same time. But technique is more than not getting hurt. It is choosing the right layer of the sun to look at. Prominence gear excels at drama in the atmosphere. The photosphere is where sunspots and granulation live, the mottled crust that a different setup can render with razor contrast. That difference turns out to be pivotal. The triangle that sets the internet on fire will not appear in Tiago's first method. It will come from a viewer using a refractor and a Herschel wedge aimed at the photosphere. Method is not trivia. Method is fate. There is also the question of time. Conjunction is not a rumor. It is a geometric fact that says you will lose the target for a while. Tiago's stream leans into that countdown. He pins the dates on screen, reads out the shrinking angles, and explains why even professional solar observatories struggle near the limb. It is not a cover story to say the sun is bright. It is navigation. So the amateur strategy becomes practical rather than romantic. Take your shots now, then let the star eat the line of sight, then pick up the trail when it returns. Can amateurs do science here, or are they playing pretend? They can, with rules. Share raw files, not polished screenshots. Provide timestamps and locations. Write down the exact filters, the exposure, the gain, the focal length. Invite others to process the same data and see if the same shapes survive. Except that most runs return nothing but heat haze. Most science is like that, even in big labs. The win is a process that lets other eyes repeat your steps and find the same thing, or fail to. Either way, reality gets sharper. A quieter transformation is happening in Tiago himself. He starts the week as a careful skeptic, with a tool that shows the wrong layer. By midweek, he is openly plotting a pivot. He will adopt the method that can see the photosphere sharply. He will buy the wedge, change the filters, and try again before the window closes. That choice is not blind faith. It is what a good investigator does when the first approach hits a wall. Change the instrument, keep the standard, keep the clock in view, and that is where we leave him for now. On a patio, under a dangerous star, with a plan that is either about to break the story open or put a myth to bed. He promises a clean replication attempt. We promise to hold him and ourselves to the rules. You promise to watch the next set of frames with the curiosity of a kid and the skepticism of a lab tech. That combination is the only way through the glare. Start with a skywide search party that never sleeps. Survey telescopes sweep the darkness for fast movers, and one night a data point refuses to behave like a local. The pipeline flags an outsider and gives it a name we can say out loud. 3i Atlas. The important word is interstellar, not born here, not staying. The orbit is hyperbolic, which in plain language means its path around the sun is open-ended. There is more than enough energy to escape, so gravity bends it, but never closes the loop. A hello, a scorching flyby, a forever goodbye. How fast is fast? Roughly 30 kilometers per second with respect to the Sunday. That sounds dramatic, and it is, but for an interstellar drifter, it sits inside the expected range. The shock is not the speed, the shock is the route. 3i Atlas arcs far inside the orbit of Mercury, skimming a realm so bright and violent that ice turns to gas in a heartbeat. At closest approach, the solar furnace becomes a physical force, hammering any exposed surface with light, heat, charged particles, and magnetic turbulence. Most fragile bodies would crack, boil, or simply come apart. So what does it look like in a camera? Think of a comet costume. A small, solid core hides at the center, and sunlight cooks it. Gas and dust billow outward to form a fuzzy atmosphere called the coma. Solar wind then combs that material into a tail that points roughly away from the Sunday. That is the script comets usually follow. With 3i Atlas, most of that script appears on cue. There is a visible coma, there is a long tail, there are jets that flick on and off as the body spins, exactly what happens when uneven patches of ice take turns facing the light. But patterns do not line up perfectly. Brightness surges snap into the light curve at moments that feel out of step with simple heating. Some observers report tail features that briefly aim toward the sun rather than away from it, which is unusual and invites arguments about viewing angle or local magnetic fields. None of this proves anything exotic. It does prove the object is interesting, which is sometimes all a mystery needs to survive through the news cycle. Here is where the split screen begins. If you live in the world of conservative astronomy, 3i Atlas is a comet from another star system getting cooked on a rude close pass. Oddities can be chalked up to composition, rotation, or complicated outgassing dynamics. If you live in the world of speculation, the same oddities become breadcrumbs. An engineered vessel might prefer a steep plunge to harvest energy, run thermal cycles in deliberate bursts, or adjust its presentation to sunlight for reasons we cannot yet guess. Same data, different stories. Only one can be true. Let us keep this grounded with one more translator's note. Hyperbolic does not mean maneuvering. It only means the path has positive energy. A rocket burn could make a hyperbolic path, but so could a rock flung inward by chance gravitational kicks over millennia. To claim intent, you would want to see systematic deviations from a gravity plus outgassing model, the kind of small, steady nudges that write their signature into precise tracking data. Until that case is made with numbers and uncertainties, hyperbolic is just a shape, not a verdict. The sun itself complicates judgment. Close to the star, the scene is noisy. Coronal mass ejections throw charged particles like weather. Magnetic fields carve and twist plasma into forms that can mimic structure. Heat pushes instruments to their limits, and that is before we add the practical problem that for a stretch of days, the object disappears into the glare from Earth's point of view. Solar conjunction is not a plot device. It is geometry. While the world is blind, stories grow. So here is our working map. Fact 1. 3i Atlas is a confirmed interstellar visitor on a one-way path through our neighborhood. Fact 2. It shows the classic signatures of a sun-warmed body venting ice and dust, layered with some behaviors that edge toward the weird. Fact 3. Weird does not automatically mean artificial. It means we have to keep both possibilities on the table while we hunt for a discriminating test. Could this all be a cosmic coincidence, or is something else going on? The next parts are going to aim that question at the triangle that sparked this chase, and at the methods that can separate plasma poetry from purposeful geometry. Picture a live chat rolling fast, emojis flying, a host narrating the routine struggle against glare and heat, then a viewer pings him with fresh frames. Chris is in Texas. He is not a lab. He is a refractor on a mount, a camera-riding shotgun, and a Herschel wedge to bleed off the sun's rage, so the photosphere pops into high contrast. He points where Thiago has been watching. He captures a sunspot group with granulation like crushed velvet, and tucked against that darkness is something the room feels before the brain names it. A triangle, not a rounded patch, not a blurred nibble. A shape with edges that hold. Thiago opens the file on stream. For a beat, everything goes quiet. The chat piles questions faster than he can read them. He zooms. The angles look clean. The sides look straight in a way that solar plasma rarely allows. He scrolls to another frame from the same run. The triangle is still there. Not identical pixel by pixel, because seeing an air boil and exposure drift, but present. He checks a third frame. The shape persists near the same sunspot architecture. It is enough to tip his posture. He leans back and lets out the line that becomes a pivot for the whole audience. Chris, you won. That sentence lands because it is a real risk. If the triangle is an artifact, Thiago has just elevated a mirage. If it is not, he has helped crack open a new chapter in solar observing. Either way, the tone shifts. This stops being a story about a smudge that might be something and becomes a story about a geometry that should not be there. The mood flips from patience to pursuit. Chris did not send only one curiosity. In another frame from the session, there is a round, dark mark elsewhere on the disk that looks too precise to be a random mottling. In a third, a ripple sweeps like a wave across a patch of texture. None of these by themselves prove anything. Together they sketch a session full of odd corners, which can mean either a rich solar day or a susceptible setup. The audience does what the internet does. Half run with the probe idea, half demand raw files and camera models and the exact wedge make and the exposure times down to the millisecond. This is where a live platform becomes a lab. Tiago does not anoint a mystery. He asks for the data. He wants the original uncompressed sequences, not screenshots. He wants the capture settings, the location, the timestamps. He wants to know whether a solar continuum filter sat behind the wedge, or whether it was a neutral density stack, whether the camera used high gain or low, whether any sharpening was applied in software before the frames were exported. The difference between a triangle and a ghost often lives in those details. Skeptics in the chat bring up internal reflections. A wedge is a prism path that can bounce a faint duplicate into the optical train under the right angles. Others mention vignetting at the field edge that can turn gradients into suspicious geometry, especially when contrast is pushed hard. A few point out that stacking algorithms and deconvolution can carve edges out of noise when parameters are too aggressive. None of these are insults. They are the checklist that keeps wonder honest. If the triangle is real, it should survive tests designed to break it. And then there is the human factor. People love patterns. The same brain that gave us mathematics also gives us faces in clouds and cities on Mars. In a chat scrolling at light speed, someone will circle a triangle in every patch of grain. That is why independent replication matters so much right now. A second observer in a different city with different optics should be able to point to the same solar region at roughly the same time and catch the same geometry. If it is a solar surface feature, it might drift with rotation. If it is a free flyer near the interstellar object's path, it might move differently. Either way, motion is a clue. Tiago tells the audience he will change tools. The prominent scope was the wrong layer for this job. The photosphere is where this signal lives, if it lives at all. He will purchase a Herschel wedge, mirror the key parts of Chris's setup, and try to replicate the session before conjunction erases the chance. That decision is less about faith and more about method. When a result shocks you, either break it or build it again. The room exhales and then surges forward. Volunteers offer cloud cover reports, seeing logs and time windows from other longitudes. A few with wedges, post-sample frames, showing how edges look when sunspots edge toward the limb, so the triangle can be compared against normal. The stream ends with a promise and a timeline. The next clear day is not just another attempt. It is an experiment with teeth. If the shape returns under stricter conditions, the story accelerates. If it vanishes under scrutiny, the story clarifies. Either outcome is progress, and that is the note the audience carries into the night. There is a place in the sky where even the boldest telescopes lose their nerve, not because people are timid, but because physics does not negotiate. When a target slides too close to the sun from our point of view, the glare floods every optic. Cameras saturate, sensors bloom, algorithms drown in scattered light. Astronomers have a simple name for this neighborhood: solar conjunction. It is the part of the story where the universe puts a hand over our eyes and says, wait, think of the sky as angles. The farther an object sits from the sun, the larger its elongation, the cleaner the view. As that angle shrinks into the single digits, the sun's brightness smears across the optics like spilled paint. A backyard rig with front-mounted solar film can safely show the sun itself, but the faint thing near it disappears, overpowered by the star. Even large observatories cannot bend this rule. The Solar Dynamics Observatory sees the sun in exquisite detail, but it is designed to watch the star, not the dim specks brushing past. Coronagraphs, such as the instrument on the Solar and Heliospheric Observatory, put a disk in front of the sun to fake an eclipse and reveal the faint corona. Yet those instruments have their own blind geometry near the edge. Between the occulting disk and the real sky, there is a region where information leaks away. So could a clever setup hack this? Not really. You can minimize scattered light with baffles and blackened tubes. You can tune filters to isolate a thin slice of light. You can stack frames to improve signal. Each trick helps a little. None of them changes the math that says a star outshines almost everything around it by many orders of magnitude. The practical result is a hard window. Before conjunction, there are days when amateurs can try to replicate a shape against the solar photosphere with a wedge and careful exposure. After a certain angle, there are days or weeks when no one on Earth can extract a clean signal at all. The countdown is not drama for clicks, It is geometry with a clock. You can actually feel the window tighten in real life. One evening, the target sits a comfortable distance from the sun, and your mount slews without stress. 2 evenings later, you are trying to hold a trembling patch of boiling texture at the limb, while the focus knob creeps and the histogram climbs. Somewhere between those nights, the line between possible and impossible is crossed. If the triangle is a genuine structure that recurs, this is when it must be caught again. If it is an artifact, this is when stricter tests will erase it. What about space? Could a spacecraft save the day while Earth is blind? Sometimes, the Solar and Heliospheric Observatory and the Solar Terrestrial Relations Observatory watch from vantage points where the sun is always in view. They excel at tracking comets that stray into the corona and at watching large-scale eruptions, but they are not tuned to resolve crisp geometry, a hair's breadth from a sunspot on the photosphere. The Parker Solar Probe dives much closer than any other craft, sampling particles and fields, yet it does not carry a camera meant to stare back at the disk for pretty pictures. Each mission has a job. None was built to babysit a rumor. Radio telescopes and radar do not help much here either. The sun is a screaming radio source. It overwhelms faint echoes and clutters spectra with storms and hiss. Even if a probe were reflecting radio waves like a small mirror, the sea of noise near the star would bury that signal. The path through conjunction is patience and planning, not brute force. There is a lesson tucked inside this blind spot that matters long after the triangle debate fades. Good investigations respect the parts of nature that refuse to budge. When reality says you cannot look for a while, the right move is to prepare. That means finishing the replication attempts before the lights go out. It means packaging raw data with time and location and gear lists so others can check it while the sun has the stage. It means scheduling the reappearance on the far side when the angle opens again and a cooler, dimmer, 3-eye atlas returns to a sky we can measure. The emotional turn is the hardest. In the silence, stories will grow. Some people will treat the blackout as proof of a cover-up. Others will declare the mystery dead. Both are shortcuts. The honest position is less satisfying and more powerful. We do not know yet. A real discovery can wait a few weeks. A real artifact will still be an artifact when the light returns. Hold the line. When the glare finally loosens and the numbers start to move again, we will be ready to separate legends from evidence. Start with what the careful people say when the room gets loud. Interstellar objects are rare, not mythical. The first to grab headlines was a skinny puzzle nicknamed Oumuamua that drifted through in 2017 and would not behave exactly like a rock. The second, called Two-Eye Borisov in 2019, looked and acted like a classic comet, coma, and tail right on cue. 3-Eye Atlas sits somewhere between those bookends, comet forward with quirks that make observers lean in but not leap. Professionals speak a different dialect than the internet. They hedge on purpose. A telescope collects spectra or brightness curves. Teams calibrate, cross-check, and argue in print. Months can pass between the discovery buzz and the careful paper that survives peer review. That lag is not a cover by default. It is the cost of getting things right when reputations and instruments are on the line. The tone is slow because the work is careful. So what does the cautious read of 3-Eye Atlas actually say? The orbit is hyperbolic, which means it came from beyond our star and is headed back out. The object shows sunlight-driven outgassing and dust that form a visible coma and a long tail. Brightness bumps and odd tail angles may reflect composition, rotation, viewing geometry, or local magnetic fields. Unusual does not equal unnatural. It just means the models need tuning once more data lands. Here is the tension that keeps the story hot. On one side, you have thousands of solar images from space and ground that never show crisp triangles on the photosphere. On the other, you have a small number of frames from a single amateur session that seem to show a geometric shape, which carries more weight. The default answer in science is always the pile of repeatable, boring, consistent data. A single dramatic outlier demands extra proof before it gets to rewrite the rulebook. The mainstream also worries about artifacts more than anecdotes. Solar imaging is hard. Instruments scatter light, filters ring, sensors bloom. Software sharpening can turn noise into edges that trick the eye. The reason professionals ask for raw files and metadata is simple. They want to separate the sky from the pipeline. If a feature is real, it survives a tour through different cameras, different telescopes, and different algorithms. If it does not, it dies in reproduction. Silence is another flashpoint. Mission accounts sometimes go quiet. Uploads pause. People fill the gap with stories. Yet there are many routine reasons why data release stalls: calibration backlogs, safety reviews, competing priorities during instrument downtime. A spacecraft team is not a newsroom. They do not push-publish every hour. Their rhythm is technical, not theatrical. That mismatch creates suspicion on fast platforms, which is understandable, but suspicion is not evidence. There is a possible bridge here. When amateurs publish clean methods and complete data, professionals pay attention. They may not join the stream chat, but they do watch. The fastest way to pull mainstream science into an anomaly is to present it in a way that fits professional workflows: timestamps, coordinates, instrument settings, unprocessed sequences, and a clear statement of what would count as success or failure. Curiosity becomes a doorway rather than a wall. So ask the hard question with a level voice. Should a handful of striking frames outweigh a mountain of normal ones? Not yet. Could they be the first hint of something genuinely new? Possibly, if and only if they meet higher standards than usual, because the claim is more dramatic than usual. That is how extraordinary evidence works. The bar rises with the stakes. There is nothing boring about that standard. It is the engine of discovery. The same caution that filters false alarms also elevates real signals when they finally pass. If the triangle survives raw scrutiny and shows up in independent runs, mainstream voices will move. If it does not, the conservative read will stand and the mystery will shrink back into intriguing comet physics. Either way, the audience wins, because the truth gets sharper and the next anomaly will face a smarter world. Start with the simple truth that the sun is not one thing. It is layers. Look with one instrument and you see fiery arches in the atmosphere. Look with another and you see the mottled crust where sunspots live. Method decides what world appears on your screen. Method also decides what kinds of ghosts sneak in when you push too hard. A prominence telescope isolates a razor-thin color of hydrogen light that sings from the chromosphere, the sun's atmospheric shell just above the visible surface. Through that window you watch looping prominences, filaments like dark ropes, and flares that curl and snap. It is spectacular and honest for that layer. But it is not the tool for surgical detail on the photosphere, the layer that looks like textured sand and hosts sunspots with crisp umbra and penumbra. The optics and filters are tuned for drama above the limb, not fine geometry against the disk. A refractor paired with a Herschel wedge is a different animal. The wedge is a prism that dumps most of the sun's energy safely out the side, so only a small fraction reaches your camera. Add a narrow band green filter, often called a solar continuum filter, and the photosphere pops. Granulation sharpens into rice grain texture. Light bridges across sunspots stand out like cracks in ice. The gain drops. The histogram behaves. That is why Chris's frames look so different from Tiago's first attempts. He was looking at the right layer with the right tool for edges. None of this makes a triangle real by itself. Every method comes with pitfalls baked in. A wedge can spawn internal reflections that paint faint duplicates near bright features. Long trains of adapters can add shiny surfaces that sprinkle lens flare into the field. Push the contrast too far in software, and you chisel noise into straight lines that never existed. Stack a run of frames with aggressive sharpening and deconvolution, and the algorithm may reward your effort by inventing detail. The sun is full of gradients. Algorithms love to carve them into shapes. Seeing matters as much as glass. The atmosphere between you and the star wriggles. On a steady morning, you can freeze short clips and recover sharp detail. On a boiling afternoon, the same telescope turns to mush. What looks like a crisp triangle in one instant can smear into a trapezoid 5 seconds later, and then into nothing as the air shifts again. That is why multiple consecutive frames are gold. A real feature does not flicker in and out on a calm timescale. It persists or it moves in a way that follows physics. Exposure is a character too. If the histogram is slammed to the right, the camera clips, highlights, and hides subtleties in a white wash. If gain is too high, random noise struts around pretending to be structure. Responsible solar imagers keep notes: aperture, focal length, filter stack, exposure in milliseconds, sensor temperature, time to the second. They share not only the pretty picture but the recipe behind it. That recipe lets a second observer bake the same cake and check if the same crisp edges appear in the same place. There is a rule of thumb that turns mystique into method. If a shape survives across raw clips, across different exposure settings, across different processing pipelines, and across different instruments at different sites, it earns attention. If it only appears after heavy contrast and unsharp masks, and vanishes when you change the kernel or the gain, it earns a shrug. This is not cynicism, it is craft. Photographers and astronomers have learned these lessons the hard way since the first glass plates. Safety sits underneath all of this. The right method is also the safe method. Front-mounted solar film or glass filters for full disc views. The wedge only on compatible refractors. Never on mirrored designs where heat can build and break things. Caps on when you leave the rig. Test indoors with a dim lamp to rehearse the capture workflow before you trust it, with the Sunday method chooses not only what you see, but whether your gear and your eyes live to see again. So when we say method matters, we are really saying that the path to truth runs through the boring parts, the focusing, the notes, the histograms kept under control, the restraint in processing, the humility to post raw clips beside your best stack. Triangles and probes make headlines. Exposure logs make discoveries. If the geometry near that sunspot is real, it will not fear these rules. It will walk through them and look even sharper on the other side. So what if the triangle is not a visitor at all? What if it is a trick of optics, wearing a convincing mask? Before we crown a mystery, we have to try to break it. Solar imaging is a minefield of elegant fakes. Light bounces where it should not. Sensors improvise. Software sharpens a whisper into a shout. The test is simple in spirit and brutal in practice. If the shape survives, attempts to kill it, keep it. If it dies under gentle pressure, let it go. Start with reflections. A Herschel wedge is a prism path that dumps heat, yet it still has interior faces. Bright features near high-contrast edges can paint a faint duplicate in the field. A diagonal or extension tube with glossy walls can add flare. The cure is rotation. Turn the camera by 90 degrees and capture again. If the triangle rotates with the sensor, you caught a ghost. If it stays put on the solar texture, it stays in the running. Now, vignetting. Many setups darken at the edges of the frame. Push contrast hard, and you carve soft fall-off into shapes that look intentional. The counter is to change framing and exposure while keeping focus steady. If the triangle morphs as the histogram shifts, it is a processing puppet. If it holds form across bright and dim runs, the odds improve. Sensor quirks can fool you too. Hot pixels, column defects, rolling shutter oddities, microlens patterns under severe light. These are shy until you push gain or compress video. Run dark frames and flat frames and note whether the same coordinates on the chip show the same mark. If yes, that is not the Sunday, that is your camera. Atmosphere turns mischief into confidence. On a poor seeing day, deconvolution can mistake boiling air for structure and carve straight lines into the shimmer. The remedy is boring repetition. Record several short clips back to back. If the triangle pops in one file and vanishes in the next, with no physical reason to leave, that is a red flag. Real features respect time. They drift or persist in ways that fit the rhythm of physics. Processing is where many mirages are born. Sharpening halos can turn gradients around sunspots into hard edges. Unsharp masks can sculpt triangles from noise if the radius and amount are too aggressive. The antidote is a blind bake-off. Share the raw clips with multiple processors who do not know what they are looking for. If independent workflows with conservative settings recover the same geometry in the same place, your signal is sturdier than a choice of sliders. Parallax and motion give you a big clue. A feature on the solar surface should ride with rotation. A flyer near the line of sight to 3i Atlas would trace a different path. Map the shape's position relative to a sunspot group over successive frames and over minutes. If it locks to the spots, think surface. If it swims against that pattern, think foreground or background or artifact. Motion that makes sense is your friend. Motion that argues with itself is a tell. Gear swaps can be decisive. Change one thing at a time. Different filter stack, different camera, different refractor. If practical, a second sight with different air and different time of day. Real phenomena are stubborn. Artifacts are parochial. They cling to a particular train of glass or a particular software habit. Timestamps and metadata matter more than drama. Write down location, exact time to the second, focal length, aperture, exposure length, gain, filter list, sensor temperature. Post that with the raw clips. This is the bridge for replication, and replication is the bridge to belief. A story that cannot be reproduced is not a story. It is a moment. there are positive tests too. Slightly defocus the image and capture again. Surface features will blur into known patterns. Ghosts and sharpening scars will often collapse or wander. Vary the exposure to bracket the histogram. Real edges should remain edges when bright and when dim. Artifacts often depend on a sweet spot in your settings. Then, set a simple pass-fail rule. Survive across raw files, across rotations, across exposure changes, across processing teams, and across instruments in different places, and the triangle graduates from curiosity to candidate. Fail any of those with a clear pattern, and it returns to the bin with lens flare and wishful thinking. This is not cynicism. This is respect for the craft that keeps our eyes honest. Maybe it is just timing. It could. Could it be the first clean glimpse of something designed near a star? It could. The only way to tell is to love the tests more than the thrill. If the triangle is real, it will not mind. It will welcome the pressure and look cleaner every time we press. So what if it is not a camera trick? What if a small craft really peeled away from 3i Atlas, dipped toward the photosphere, and charged its batteries at the biggest power plant in the neighborhood? The idea sounds wild until you run the numbers. At Earth, the sunlight that reaches a square meter is roughly 1 1/3 kilowatts. At 1/10 of that distance, near the path discussed for 3i Atlas, the same square meter is bathed in about 100 times more power. Call it 130,000 watts per square meter, give or take, depending on exact distance and angle. Now imagine a compact collector, not a city-sized array, something closer to a building footprint. If a triangular panel 100 meters on a side presented itself to the sun, its collecting surface would be on the order of 4,000 square meters. Multiply that by the irradiance near 1/10 of an astronomical unit, and you get hundreds of millions of watts of raw sunlight. Even after you subtract for reflectivity and conversion losses, you are still looking at tens of megawatts available in real time. That is, aircraft carrier power in a package small enough to hide in a solar image. So, the power is there. The problem is everything else. Temperature wants to climb toward brutal numbers. Radiation bakes electronics. Charged particles pound surfaces. Any real collector would need a way to reflect most of the energy it cannot use, dump heat aggressively, and keep delicate parts behind a shield that does not melt. Humans do a baby version of this already. The Parker Solar Probe flies much closer to the sun than any spacecraft in history, and survives by hiding behind a carbon-based heat shield while only peaking instruments around the edge. It uses carefully chosen trajectories and short exposure times to limit stress. It also routes heat away from what cannot get hot. A hypothetical probe would need similar tricks, just scaled for different goals. The collector might be highly reflective in visible light to keep from overheating, while being selectively absorptive in a narrow band tuned for conversion. It might pump heat to radiators shaded from direct sunlight, so they can glow energy into deep space. It might carry materials that are refractory, which means they keep their strength at temperatures that would ruin aluminum and steel. None of this is magic. It is hard engineering that pushes toward the edge of what we know and then steps beyond. Could a craft ride close to the photosphere without being torn apart by magnetic chaos? Maybe, if it lives in the boundary region where the plasma is still dominated by the surface pattern and not by eruptive loops, and if it chooses short visits rather than long loiters. It could also choose its path to skim regions with calmer fields at that moment, the way pilots pick their altitude to dodge turbulence. If you can measure the magnetic structure in advance or in real time, you can pick lanes that are survivable. Would an energy harvest leave footprints that our cameras or instruments could notice? It might. A polished planar collector could throw glints that change brightness with viewing angle. A power system might shed waste heat in the infrared band in a way that stands out against the solar background if the geometry is right. If the craft interacts with the solar wind, it could carve a tiny wake or produce a subtle ripple where flowing particles meet a manufactured field. These are small effects against a roaring background, but small is not the same as impossible. There is a quieter clue: behavior. A refueling pass is purposeful. You would expect coordinated motion rather than random drift. That could look like a shape that holds a fixed orientation relative to the sun while translating along a path that makes thermal sense. It could look like timed approaches that repeat at the same phase of the larger object's orbit. It could look like brightness rhythms that track a power cycle rather than the simple heating curve of ordinary outgassing. And yet the mundane explanation fights back well. Comets can vent in jets that switch on and off as they rotate, which can mimic controlled pulses of activity. Sunspots and their motes can form sharp-edged contrasts that look geometric when processed hard. Internal reflections can paint shapes that hold for a few frames when the scene is high contrast. This is why the hypothesis is not a conclusion. It is a target for tests we can actually run. So we ask the practical question: if a probe were refueling, what could we test from here? Look for repeatable geometry across observers and instruments. Look for motion that is coherent rather than jittery. Look for angle-dependent glints that change as the sun viewer geometry changes. Look for any hint of waste heat when the field of view and instruments allow. Most will come up empty. That is fine. A single clean success that survives replication would carry far more weight than 100 maybes. Could this all be a cosmic coincidence? Absolutely. Could it be our first glimpse of a technology that treats a star the way sailors treat a harbour? Also possible. If difficult, the power is real, the environment is harsh, the way forward is simple. Hunt for signatures that technology cannot help leaving behind, and demand that each one repeat. If the triangle is a collector, it will not just look sharp, it will act deliberate. Silence is a character in this story. It walks in during countdowns and makes every pause feel like a verdict. When uploads slow and dashboards go dark, the internet fills the gap with meaning. If a triangle appears and the agencies take their time, the quiet can sound like a cover story. If you sit on a mission team staring at safety limits and calibration logs, the same quiet sounds like discipline. Same pause, two very different readings. First, the boring world that rarely trends. Space hardware breaks and gets tired. Teams rotate. Pipelines jam. A sensor gets a temperature drift, and every image must be rechecked against new baselines so that a dust mote is not mistaken for geology. A flight computer goes into safe mode, and the priority becomes recovery, not press releases. Even when everything works, raw frames are not the truth. They pass through flat field corrections, cosmic ray rejection, and geometric fixes. Each step demands a human sign-off, and humans are finite. That is not malice, that is maintenance. Now, the emotional world that never sleeps. A dramatic claim lands on social feeds and a countdown clock ticks in the corner. Viewers want an answer today. A triangle splashes across a stream. The idea of a probe refueling near the sun is either thrilling or terrifying, often both. In that headspace, every hour without a new post feels like proof. Proof of fear, proof of control. Proof that someone somewhere knows and will not say. Our brains are built to finish stories. Silence invites us to finish them with whatever fits our priors. There is also a history problem. People remember moments when institutions moved slowly on surprising results. Some were caution and turned out wise. Some were politics and turned out embarrassing. That memory colors the present. A delay that would be invisible during a quiet season becomes suspicious during a viral week. The same 48 hours taste different when a triangle is trending. So what do we do with that tension? We ask for receipts, not vibes. If you think a data hold is nefarious, look for concrete patterns that persist beyond a single week. Are there public gaps that align neatly with every controversial moment, yet never with routine maintenance? Do official statements contradict publicly known instrument schedules? Can you point to past releases from the same team that moved faster under similar technical conditions? If yes, suspicion earns weight. If not, the simplest answer makes more sense. Pipelines are slow for real, boring reasons. On the other side, agencies can meet the moment without feeding hype. A short status page with honest notes helps a lot. Imaging paused while we check calibration on the detector. Expect an update next week. Here is a link to last month's processing queue so you can see typical pace. That kind of daylight is not a concession to conspiracy. It is an investment in patience. People will still speculate, but now the blank space has dates and reasons. There is a deeper reason to be careful with silence. It can tilt communities toward the answer they want before the data is ready. In a chat scrolling at high speed, it is easy to treat absence as confirmation. We begin to phrase the story in past tense. We knew it. They hid it. That is how a maybe becomes a belief, without ever passing through evidence. When the real files finally land, minds have already hardened. No one wins in that outcome, so we propose a middle path for this audience, and for us. Assume incompetence before conspiracy, and still demand clarity. Respect the constraints that keep instruments alive, and still push for timelines. Celebrate the boring posts that explain why a frame was scrubbed. When a gap stretches longer than the norm, ask for the reason and then wait for the answer rather than inventing one. Curiosity without patience is a rumor factory. Patience without curiosity is a nap. The triangle legend will either shrink under replication or grow into something history books remember. Silence alone does not choose that path. Data does. If a shape survives across raw clips and across observers, the quiet corners of the internet will not be able to contain it. Professional teams will turn and point. Papers will appear. Arguments will sharpen where they belong, on plots and error bars. If the shape evaporates under gentle tests, no volume of silence will rescue it. Maybe it is just timing. A rumor that grew in the hours when nothing new was posted. It could. Could a pause also reflect a careful team refusing to rush a story that would travel the world in minutes? Yes. The only way to hold both truths is to love updates that say nothing exciting. Those are the guardrails that keep us from driving off the road. When the news breaks for real, we will hear it in the only voice that matters here, the voice of repeated results. Hold up a pair of sunglasses and twist them in front of a window. The glare fades, then returns, then fades again as you turn the lenses. That trick works because the light is polarized. It means the electric field of the light is no longer jumbled in every direction. It leans. It lines up. Space telescopes and big ground instruments can measure that lean with sensitive detectors. When sunlight bounces off tiny grains of dust, the amount and direction of polarization tell you something about the grains. Size, shape, texture, even how fluffy or compact they are. Now bring that tool to 3i Atlas. Observers have reported polarization values that sit at the edge of what is typical for comets. Not way outside, not a smoking gun, just a little odd. Think of it like a fingerprint that smudges in an interesting way. You do not arrest anyone for a smudge. You look closer. In plain terms, dust a little larger or a little shinier than usual can boost polarization at certain viewing angles. Dust that is oddly shaped or has a crust of dark carbon can do the same. When the object swings around the sun, the angle between the sun, the object, and Earth changes. That angle is the phase angle, and it controls how strong the polarization looks. If the curve of polarization versus phase angle is smooth and sits near the family of known comets, the conservative story gets stronger. If the curve bends in a way that does not match the comet family, then eyebrows go up. Could engineered surfaces mimic this? Yes, in theory. A uniform coating or a deliberately roughened panel might scatter light in a way that looks strange compared with dusty snow. A polished face might even produce bright flashes when the geometry lines up. But now we are stacking a lot of ifs. To move beyond stories, we need patterns that data can bite. So what would push this part of the case forward? First, more than a single night. You want a sweep of measurements across many phase angles as the object approaches and recedes. That turns one number into a curve that you can compare with a library of comet curves. Second, more than one color. Measure in red light and green light and blue light. Natural dust often changes polarization with color in familiar ways. A manufactured surface could behave differently. Third, independent teams. If 2 or 3 groups using different instruments see the same curve with similar error bars, the signal is real. If the results disagree wildly, the signal is noise or calibration. There is another clue tucked into the data that almost never makes headlines. Polarization can be mapped across the coma and tail, not just measured as a single total. If you make a small image where each pixel carries a tiny arrow that shows polarization, direction, and strength, patterns emerge. Jets from a spinning comet can leave swirls and stripes in that map. A rigid object reflecting sunlight might stamp a cleaner, more geometric signature. Think of it as contour lines on a topographic map. Nature draws messy hills. Engineering loves straight roads. The triangle rumor sneaks in here too. If a geometric object truly sat near the photosphere during the observation window, it would be drowned in the sun's own light. Polarization measurements focused on the comet's dust would not see that triangle directly. What they can see is whether the dust behavior around 3i Atlas is ordinary or not. If the dust looks textbook, then any triangle claim has to stand entirely on imaging tests. If the dust looks unusual in a coherent way, the door opens wider for exotic interpretations, though it still does not force them. Let us not forget the hard limits. Polarization is fussy. Small misalignments can skew results. Atmosphere can add a little extra twist to the light. Instruments must be calibrated with known standards before and after each run. Teams often spend more time proving their numbers are clean than they do on the sky. That is why a single surprising value should never carry a grand conclusion. Curves do, replication does. Imagine the next few months after conjunction ends. The object returns to a friendlier angle. Observers clock a series of polarization points and the curve starts to trace itself. If it hugs the comet family, the alien surface story loses a pillar. If it peels away in a repeatable, color-dependent pattern, calls will go out to point more instruments and gather more light. Either path is a win, because loose speculation becomes a test you can pass or fail. Could this all be a cosmic coincidence? The edge of normal that only looks dramatic because the rest of the plot is loud? Absolutely. Could it be the first hint that dust from another star does not play by our usual rules, or that something reflective rides within the haze? Also possible. The way through is not a single number on a slide. It is a curve drawn with patience and checked by strangers. When light lines up, it is telling you a story. Our job is to listen long enough to hear the whole sentence. Breathe on a cold window and you leave a foggy print. Comets do the same thing in sunlight. Spectrographs split that glow into colors and reveal fingerprints of molecules in the haze. For 3i Atlas, the lines that rise above the noise are familiar. Water vapor, fragments of water called hydroxyl, carbon monoxide, and other volatiles that boil off when ice is warmed. This is the standard heartbeat of a comet under stress. Gas production climbs as distance to the sun shrinks and then eases as the object glides away. That pattern matters because chemistry is hard to fake. Water's signature is so specific that instruments on different telescopes can agree even when they disagree on brightness by a notch or two. The same goes for carbon monoxide and the family of simple compounds comets carry. When multiple teams report the same lines at the same time, within honest error bars, the safe conclusion gains weight. Nature knows how to make this spectrum, so does a detection of volatiles slam the door on anything artificial? Not necessarily. An engineered object could carry ice on purpose. Water is a ruthless heat sponge. When you let it vaporize, it drags heat away and leaves the structure cooler than it would be without that sacrificial layer. Human missions have flirted with this idea for extreme environments. Think of a shield that sweats. A craft designed for a solar pit stop could use a thin blanket of ice as both coolant and camouflage, letting it behave like a comet while it gets work done. But possible is not the same as likely. The more the chemistry of 3i Atlas matches the chemistry of ordinary comets, the harder it is to claim technology. Ratios tell the story here. The balance between water and carbon monoxide. The presence or absence of certain organics. The way those ratios change with distance from the sunday. Most comets cluster in a few familiar neighborhoods of that map. If 3i Atlas lives in one of those neighborhoods, the conservative reading strengthens. There are subtle clues in how the light varies. When outgassing drives brightness, you often see a correlation between the strength of a molecule's line and the overall light curve. When jets turn on, the comet brightens and the lines stiffen. When jets turn off, both relax. A machine would not care about those natural rhythms. It might pulse in a different cadence. It might release heat at moments that do not match the curve you would expect from simple solar cooking. Watching for those mismatches is fair game. Isotopes can sharpen the edge even more. Hydrogen comes in a heavier flavor called deuterium. The ratio of deuterium to hydrogen in comet water is a subtle tracer of where that ice formed long ago. Solar system comets have a spread of values that scientists have logged for decades. An interstellar visitor could carry a ratio that sits outside our local pattern but still make perfect sense for a different nursery. That would be thrilling and still natural. A ratio that hops around wildly from night to night would be stranger and might point to calibration rather than cosmic weirdness. All of this depends on clean spectra. That is not easy near the sunday. The sky glows, instruments get pushed, lines can be contaminated by scattered light and must be untangled with careful subtraction. That is why independent confirmation matters. 2 or 3 teams reporting similar strengths and trends turn a tempting hint into something steady enough to lean on. The triangle rumor touches this chapter only at the edges. A small geometric object near the photosphere would drown in the star's own glow. It would not announce itself in the comet's spectrum unless it ejects material of its own. So chemistry is mainly a test of the parent object. If the parent looks textbook by composition, and by how that composition changes with distance, the burden on the triangle grows. Imaging would have to carry the claim by itself. Could a deliberate design hide inside a natural shell? It could. A vehicle might anchor itself in a lump of dirty ice and ride the physics of a comet to stay anonymous. It might even exploit outgassing to steer without obvious thrusters, the way a sailboat tacks in wind. If that is the game, then chemistry remains ordinary, while behavior gives the trick away. That is why this series moves back and forth between spectra and motion. One tells you what the thing is made of, the other tells you what the thing is trying to do. Here is the simple rule for our shared investigation. When composition looks normal, the extraordinary claim faces a steeper climb. When composition looks odd in a repeatable way, the door opens wider. Either way, we win by asking the sky for numbers that a story cannot bend. After conjunction, when the angles soften and the glare relents, those numbers will flow again. If 3i Atlas breathes like a comet, we will say so. If it breathes like something else, we will say that too. Imagine throwing a ball and predicting exactly where it will be at every heartbeat. Gravity does most of the math. If the ball drifts a little from that perfect path, you look for a push you forgot to include. Astronomers do the same thing with interstellar visitors. They fit a gravity-only path that includes the pull of the sun and planets. Then they measure the difference between where the object should be and where it actually shows up on the sky. Those tiny differences are called residuals. In those wiggles live the fingerprints of gas jets or something stranger. Here is the plain version of a hard problem. Precision astrometry is just careful point-taking. You timestamp an exposure to the second. You measure the dot's position against a calibrated star field. You repeat this across nights and across telescopes. Fit a clean gravitational arc and subtract. What is left should look like noise that bounces around zero. If you see a steady drift that grows in one direction, you have a force. If you see curves that reverse with a rhythm, you might be watching seasonal jets that turn on as the body spins. Outgassing writes a distinctive signature. Imagine a lumpy snowball that warms unevenly. As it rotates, different patches of ice face the sun and vent. The thrust is tiny, but it adds up. The push is strongest when the object is closer to the sun, and it tends to point a little away from the star, or a little along the path, depending on geometry. In residual space that looks like a smooth bias that grows near closest approach, then fades. If the rotation is known, you can even see a faint beat that lines up with that spin. Artificial control would not have to follow those rules. A deliberate burn could happen when the heating is weak. It could push sideways to change inclination rather than speed. It could happen in short pulses that step the path rather than curve it gently. In residuals that would look like kinks or plateaus, like a tidy S shape that arrives out of sync with sunlight, a light sail would be different again. Sunlight itself would push the object in a way that scales with the square of distance. That effect would not care about water jets. It would care about area compared with mass and about orientation. Here is the catch that trips up overeager plots. Residuals live and die by error bars. Near the sun, the sky background is harsh. Stars used for calibration get washed out. Centroids shift when a fuzzy coma smears the dot. Clocks on some rigs are not disciplined to the second. Atmospheric refraction near the horizon nudges everything a little. If you do not track those small gremlins, a fantasy force appears where none exists. This is why honest astrometry reports carry uncertainties, and why the best fits give the same answer when someone else re-reduces the same images. So what would count as a real push on 3i Atlas? First, a consistent pattern across independent observers using different optics and different nights. Second, a curve that a simple gravity model cannot absorb even when you add the usual comet jet terms. Third, a time history that lines up with a physical cause. If you claim outgassing, the deviation should swell as the object nears the sun and relax as it leaves. If you claim sunlight pressure on a thin body, the deviation should scale smoothly with distance and with orientation implied by light curve glints. If you claim propulsion, show a step or arc that does not care about solar distance and repeats with intent. Brightness can help. When a comet vents harder, it often brightens. If residuals grow on the same nights that specific gas lines strengthen, that supports the jet story. If the object is steady by chemistry, yet the path still pushes, you look harder at sail like behavior or at bad data. Motion and composition need to talk to each other. When they disagree, one of them is lying or something interesting is happening. There is an elegant cross-check anyone can understand. Plot the differences in the direction toward the sun, in the direction along the path, and out of the orbital plane. Outgassing tends to bias the first two. Sunlight pressure on a wide, thin object can load the second and sometimes the out-of-plane direction if the body tilts. Smart thrusting can do anything it wants, which is exactly why it must leave a human pattern rather than a thermal one. A machine is tidy even when it tries not to be. What about the triangle near the photosphere? Residuals mostly test the parent object. A small craft skimming the sun could leave no trace in the larger body's fit, the same way a rider on a motorcycle does not change the highway's shape. That is fine. We need both kinds of evidence. If the big traveler shows only natural pushes while the small shape behaves like a rigid body with coherent motion, the case splits into two parallel tracks. If both lines point to ordinary physics, the extraordinary story loses air. After conjunction, the path opens again. This is where serious amateurs can shine. Use disciplined timing. Keep exposures short enough that the dot is a point, not a streak. Calibrate against modern star catalogues. Report uncertainties with the same care you give the numbers. Submit to public databases so multiple teams can refit the arc. If there is a force, we will see it as a chorus, not a solo. If there is not, the residuals will flatten into noise, and the mystery will move to images and spectra where it belongs. Could this all be a cosmic coincidence? A pattern teased from a few noisy nights? It could. Could it be the first clean hint that something is steering rather than boiling? Also possible, the way to tell is to stop treating the plot like a horoscope and start treating it like a ledger. Every deviation needs a receipt. When the numbers balance, the story will finally have to choose a side. Turn a live stream into a laboratory, and you get speed, eyes, and energy. You also inherit noise, bias, and the urge to win the argument before the data is ready. Crowd science is powerful when it acts like a team, and dangerous when it acts like a rumor. The fix is not to slow down curiosity. The fix is to give curiosity rails so it can sprint without flipping. Start with the rule that keeps communities honest. Make predictions before you look. Say where the triangle should be on the next clear morning, how far from the nearest sunspot, what orientation, and how it should drift if it rides solar rotation. Post the prediction with a timestamp, then collect the frames. When results land, they land against a promise, not a hunch reshaped after the fact. Pre-committed guesses break the spell of hindsight. Next comes blind processing. Share raw clips with several processors who do not know what they are hunting. Ask them to run conservative settings and return whatever features survive. If each person with a different workflow recovers the same geometry in the same place, confidence rises. If only the person who believes in a probe sees a triangle, the signal smells like bias. You do not need perfect statistics to learn from this. You only need strangers who agree to keep their hands light on the sliders. Documentation turns passion into reusable work. Every capture session should travel with a one-page sheet that lists location, time to the second, telescope type, focal length, filter stack, exposure, gain, camera model, and a note on seeing. Add a short line about weather and wind. Record whether the camera was rotated between runs. That tiny packet lets another observer repeat the setup or catch a hidden flaw. It also makes your best frames admissible in any professional inbox you send them to later. Moderation is a tool, not a mood. Fast chats reward hot takes, so build quiet rooms where the work happens. Pin the current method, not the latest meme. Separate speculation threads from data threads. Archive the raw files somewhere public, then link them at the top of every discussion so new joiners can pull the originals without begging. Keep a short glossary so newcomers learn the difference between a prominence and the photosphere in 10 seconds. The point is not to gatekeep, the point is to teach at the speed of excitement. Invite skeptics like you, invite specialists. Give them a lane to try to break the claim. A respected contrarian who shows their work raises the bar for everyone and keeps believers from drifting into wishful editing. Celebrate clean nulls. A night that proves a processing artifact is not a failure. It is a map of what not to do next time, and it saves 100 people from repeating the same mistake. Safety is not optional. Solar work can cook sensors and eyes. Publish a basic safety checklist at the start of each campaign. Front-mounted solar film or glass for full disk imaging. The wedge only on compatible refractors. Never leave a live scope pointed at the sun without a cap. If in doubt, stop. The fastest way to lose a community is to hurt it. Time matters, and so does shared time. Agree on a reference clock for logs. Even a phone locked to a network time service will do. When observers in different longitudes capture the same region within minutes of each other, alignment becomes easy. A cluster of nearly simultaneous clips that show the same geometry is more convincing than a single perfect frame that no one can match. Beware the highlight reel. Social feeds love a neat edge and hate a smudged truth. For every viral image, publish the companion stack that shows the surrounding minutes and the nearby frames where nothing dramatic happened. Put the boring context next to the spike. This habit disarms cherry-picking and trains the audience to love full stories, not just screenshots. Build small tools that make good behavior easy. A file name template that encodes time, gear, and exposure. A short script that extracts camera settings into a text file. A shared sheet that logs who is watching which solar longitude on which day. The goal is a quilt, where each square is labeled and aligned. When the quilt is big enough, patterns appear that no single observer could have seen. Most of all, guard the culture. Reward people who change their minds in public when a better method wins. Stick a gold star on the post that kills a fun error with gentle clarity. Curiosity plus humility as a force. Curiosity without humility as a storm. Could a crowd catch a real triangle near a star? It could, if the crowd becomes a method. Could the same crowd convince itself of a phantom? That happens daily. The difference is a handful of habits that turn adrenaline into evidence. Keep the rails. Keep the receipts. Keep the door open to anyone who brings light, and keep a kind hand on anyone who brings heat. Here is how we turn a striking picture into a measurable claim. We do it like engineers on a deadline. Define the target, lock the clocks, change one variable at a time, then let the sky decide. If the triangle is real, it will reappear under stricter conditions and behave in ways that match physics. If it is a ghost, the method will wash it out. Either way, truth gets a clean lane. Start with the same solar real estate. Use yesterday's sunspot group as your anchor, not memory. Pull a current full disk image from a reputable source and mark the coordinates of the target region on the photosphere. Convert that to your local mount's pointing so you can return to the exact texture, not just the neighborhood. Replication begins with the same patch of star. Now, lock time. Set your capture window to straddle the same local solar hour when the first report landed. Then bracket a little earlier and a little later. Use a disciplined cadence. For example, 10 clips of 30 seconds each, separated by 10 seconds, then repeat the set. That rhythm gives you a timeline for motion tests and protects you from one lucky or unlucky frame. Keep a simple rule on the wall. One image is a picture, a sequence is evidence. Instrument discipline matters. If you are using a refractor with a Herschel wedge, record the exact filter stack and camera settings. Run a quick rotation test at the end of the first set. Turn the camera by 90 degrees and capture the same region again. If the triangle rotates with the sensor, you bagged an internal reflection. If it stays with the sun's texture, it earns another breath. Do not forget a brightness bracket. Run a few clips, one stop brighter and one stop dimmer. Real edges persist across modest exposure swings. Artifacts often depend on a sweet spot. Motion is your biggest ally. A feature on the solar surface must ride rotation. Map the triangle's position relative to the nearest sunspot features across your sequence. If it drifts with the spots at the right rate and direction for that latitude, you are likely looking at a surface phenomenon, not a free flyer. If it drifts against that pattern, measure that drift and compare it with what you would expect from an object near the line of sight to 3-eye atlas. Coherent motion in either frame is a clue. Wandering that argues with itself is a tell. Do a gear cross-check without breaking the scene. Swap only one thing. Change the green continuum filter for a different narrow band of similar width. Or swap cameras while keeping optics fixed. Or change focal length by a small, known factor. If the geometry scales predictably and remains in place, the signal hardens. If it warps or vanishes when you touch a single component, you are probably wrangling a pipeline quirk. Real phenomena are stubborn. Artifacts are provincial. Invite an independent observer to shadow you. Coordination beats solo heroics. Two sites imaging the same region within minutes of each other will either see the same geometry or they will not. If both do, the odds tilt fast. If only one does, look hard at the differences in seeing, exposure, and processing. Do not argue first. Compare notes first. Process light. Publish heavy. Share the raw clips, not just the prettied stack. Post timestamps to the second, location, focal length, exposure, gain, filter list, sensor temperature. Include a one-line weather note on seeing and wind. When strangers can take your raw files and recover the same geometry with conservative settings, you have left the rumor basin and stepped into the river that flows toward journals and telescopes with longer names. Set a pass-fail matrix before you press record. Pass requires the triangle to appear in multiple consecutive raw clips in the same solar region to survive camera rotation and exposure bracketing, and to exhibit motion that matches either surface rotation or a coherent non-surface path. Bonus points if a second sight sees it too. Fail is any clean violation of those expectations, or dependence on sharpening halos or extreme contrast. A null night is not a fail, it is a data point that narrows the path. Respect the clock. If conjunction is imminent, publish fast and clean. Put raw, notes, and quick look stacks in a public folder so the next clear morning on another continent can pick up where you left off. A distributed relay beats a single sprint every time. Give the next observer your baton with timestamps, not vibes. Here is the mindset that keeps you honest. Love the test more than the triangle. Celebrate a replicated shape because it survived pressure. Celebrate a vanishing shape because the method did its job. Science is not a spotlight that blesses a theory. It is a filter that keeps what is sturdy and lets the rest fall away. Run the plan. Let the star answer. When a mystery gets loud enough, the big instruments start listening. The Solar Dynamics Observatory stares at the sun all day from space and builds a time machine of images you can rewind. The Daniel K. Inouye Solar Telescope on Earth resolves magnetic threads thinner than the blade of a kitchen knife when the air is steady. The Parker Solar Probe dives close enough to taste the wind of charged particles. The European Space Agency's Hera mission flies through the inner system with sensitive cameras and dust sensors that sometimes pick up happy accidents. None of these machines were designed to chase a single rumor, yet all of them can cross the story if the evidence sharpens. First, aim for what fits their jobs. The Solar Dynamics Observatory is perfect for checking whether the photosphere near a sunspot showed any odd patches at the time of a triangle claim. Its public archive lets anyone pull the frames. If a rigid geometry sat on the surface, the sequence should show a consistent feature as the sun rolls. If nothing is there, that narrows the options. No drama required, just a rewind and a look. Inouye is a different beast. It is a pointed scalpel, not a wide net. Time on it is precious and scheduled for specific research goals. It will not chase a screenshot. It will respond to a testable target. That is where amateurs can help. A packet that includes raw sequences, precise coordinates on the solar disk, times to the second, and a note on expected motion builds a case that the instrument can actually use. You are not pitching a vibe, you are pitching a coordinate and a clock. Parker does not take pretty surface pictures. It swims through plasma and fields. That means it could catch indirect hints if a region near the sun behaved oddly while it was nearby. A sudden spike in dust counts. A magnetic kink that does not fit local models. You would not hang a conclusion on that alone, yet a time-stamped oddity can point other eyes in the right direction and justify a look through imaging archives for the same moment. Hera is focused on a binary asteroid, but spacecraft often log more than their main target. If its flight path crosses debris from 3i Atlas, its dust analyzer might record particle sizes or compositions that feel off. Again, this is serendipity. Missions do not swerve on a whim. They sometimes notice more than they planned whenever the universe lines things up just so. The bridge between people on patios and people running observatories is built from data that travels well. That means standardized time, world time to the second. That means coordinates referenced to an easy-to-check source, such as a full-disk solar image with a simple grid overlay. That means an honest log of gear, exposure, gain, filters, and any processing notes. One page. Clear. Repeatable. You are not trying to impress. You are trying to let a stranger reproduce your view. There is also a workflow that earns attention. Put the raw frames in a stable public location. Add a short README that explains the file naming scheme. Include a quick look stack that shows the triangle in context and a couple of nearby frames that do not. Post a measured position of the shape relative to a sunspot group with uncertainties. Link to any independent repetitions from other sites. Then send a short note to the solar community lists that says what you saw, when you saw it, and what would count as a refutation. You are inviting a check, not a cheer. Expectations matter. Professionals will not endorse a claim because it is exciting. They will try to break it. That is good. A feature that survives contact with critical people carrying better instruments becomes real. A feature that fails those encounters becomes a lesson in optics that will save everyone time next round. Either way, you win by moving the conversation from a feed to a lab. There is a role for this channel too. We can stitch the quilt. We can host the packets that meet minimum standards and tag them by time and solar longitude. We can nudge volunteers to fill holes in coverage when a region is underwatched. We can mirror the public archives and publish clear instructions for how to search them, so a student with a laptop can pull the day a claim was made and verify whether the sun itself remembers anything unusual. The best part is that none of this requires permission to begin. It requires patience, precision, and a little humility. When amateurs bring receipts, professionals listen. When professionals share clear reasons for a no, amateurs learn faster. The triangle story will either fade as an artifact or harden into a real clue. In both outcomes, the bridge we build now will carry the next anomaly. That is how a backyard and a billion-dollar telescope end up on the same team. Imagine a tireless assistant that never blinks. It watches every frame from every telescope, compares each pixel to a memory of what the sun usually does, and raises a hand the instant something refuses to fit. That is the promise of machine learning when it is used with care, not magic, not proof. A fast and disciplined lookout that turns oceans of footage into a shortlist we can test. Start simple. Teach a model what normal looks like. Feed it thousands of images of the photosphere and the atmosphere from public archives. Let it learn the rhythm of granulation, the ragged edges of sunspots, the flutter of seeing, the artifacts that come and go with bad air and hot sensors. Then give it new frames and ask a blunt question. Can you recreate this scene from your idea of normal? When the answer is yes, the model redraws the picture easily. When the answer is no, a reconstruction error rises. That spike is not a verdict. It is a flag that says, look here first. Now the hard part. A reckless model will flag everything. It will scream triangle at every crisp edge, circle at every dust mote, anomaly at every gust of wind. The cure is a ladder of checks. The first rung is a shape model that has been trained to ignore ordinary solar geometry. The second rung is a motion test that looks for coherent drift across a run rather than single-frame shocks. The third rung is a redundancy rule. No alert survives unless two independent observers within a short window catch a related feature in the same solar neighborhood. One telescope can fool you, two in different air with different glass are harder to fool. There is a trick to keeping bias in a cage. Build the system without telling it what triangles are. Let it learn normal first through unsupervised practice. Only after that do you add a small set of known artifacts and a small set of controlled synthetic shapes to teach it restraint. Too many examples of the exotic and it hallucinates. Too few and it misses the point of the exercise. Balance matters. Transparency matters even more. Every alert should travel with a tiny dossier, time to the second. A checksum for each raw clip so anyone can verify nothing was altered. The model version that produced the flag, the confidence score, and the reasons it gave, expressed in plain words. Brightness changed by this much across frames. Edges remain straight under two different sharpening settings. Motion tracks this many pixels toward the limb. When a stranger can read the dossier and rerun the test, trust goes up. When an alert is only a screenshot and a claim, trust falls apart. False alarms are not failure. They are training data with a sense of humor. Keep an open logbook of mistakes and push those back into the pipeline so the model learns to stop chasing them. Publish the negative controls alongside the hits. If the system never admits to a miss, it is lying. If it can show how it learned from one, it grows up fast. A good pipeline respects people. The model does not get the last word. It proposes. Humans dispose. Experienced processors rerun the raw clips with conservative settings and decide whether any geometry survives. Coordinators check for near-simultaneous captures from other longitudes. If the alert clears those human gates, it graduates to a public candidate with coordinates and a clock so others can try to catch it again. The machine is a scout, the crowd is the cavalry, speed is the real gift. A watcher that combs 1,000 frames in minutes can notify observers while the sun is still in range. That means a quick pivot in a backyard, a short call to a friend, a time zone away, a second lens pointed in time to confirm or refute. Instead of a rumor that grows for days, you get a test that runs in hours. There are guardrails we should not skip. Freeze the model during a campaign so its behavior does not drift while people are depending on it. Keep a small verification set hidden from training so performance claims are honest. Rotate the camera occasionally just to see whether the alert turns with the sensor, which would betray an internal reflection. And never let a threshold be set by vibes. Tune it on labeled truth and on fully documented failures. Could an algorithm be the first to notice a real triangle near a sunspot? It could. Could the same algorithm spam us with ghosts if we point it poorly? That happens every day when people chase novelty more than rigor. The way through is a partnership. Machines handle the deluge. Humans handle the doubt. Together they build a paper trail no single screenshot can fake. If the triangle is real, a disciplined pipeline will not only find it, it will find it again tomorrow, and it will tell us exactly when and where to look. If it is not, the same pipeline will drown it in a sea of ordinary sun and teach us to stop seeing shapes that are not there. Either way, the future of this hunt is faster, more open, and easier to check. The tireless assistant is already awake. It is time to give it good rules and send it to work. Imagine the test running clean from start to finish. Independent observers in different cities point at the same sunspot group, minutes apart, and each records a sharp triangular shape that persists across back-to-back clips. The camera rotates, and the triangle does not. Exposure shifts brighter and dimmer, and the edges hold. Processing is conservative, with light sharpening at most, and the geometry is still there in the raw. Motion maps show a path that fits physics rather than jitter. At that moment, the rumor hardens into a candidate. What happens next is not fireworks, it is paperwork, and it is thrilling if you love truth. Observers package their raw clips with timing to the second, instrument lists, focal lengths, filter stacks, and weather notes. They publish measured positions of the triangle relative to sunspot features with uncertainties. They post simple plots that show the shape's drift over minutes. A short summary explains the pass rules it met. Anyone with the files can rerun the stack and recover the same edges. That portability is the first badge of reality. Now the search expands. Public solar archives get a rewind. People comb the Solar Dynamics Observatory frames from the same window and look for a matching mark at the same coordinates. If the shape sits on the photosphere, it should ride rotation across the day. If it is a free flyer, it should not be locked to surface flow. Either result is valuable. A surface-linked triangle is a solar physics puzzle. A free mover is something else entirely. Optics tests give the image a second life. Glint hunting begins. A rigid, reflective surface can throw flashes that brighten or dim as the angle between sun, object, and viewer changes. Teams compare brightness across sites and look for the same rhythm. A spin could reveal itself as a repeating pulse. If there is waste, heat, infrared, instruments at the right wavelengths might catch a faint excess compared with the surrounding photosphere. Though this is a steep challenge against a blazing background, even a hint that repeats would push attention higher. The motion record becomes the spine of the case. Plot the triangle's position every few seconds through a sequence and fit that path. Does it drift with the surface at the correct rate for that latitude? Then we have a magnetic or thermal structure that mimics geometry, which is fascinating in its own right. Does it slide against rotation at a steady pace that matches the known track of 3i Atlas? Then we are watching a traveler near a traveler. Does it hold orientation while translating, the way a vehicle would keep a panel pointed at the star while it moves along a lane? That is the most provocative answer, and the riskiest to claim without ironclad numbers. At this stage, professional interest switches on. A short, clear note goes to solar and heliophysics lists with links to raw data and to the simple motion plots. The note does not sell a conclusion, it sells coordinates, times, and a testable claim. If the triangle sits on the surface at these positions over these minutes, the Solar Dynamics Observatory should have seen it. If the triangle moves with this drift against rotation over this span, here are the predicted locations for the next hour. A few well-aimed sentences can win a look from better instruments. Peer review is not a brick wall, it is a gate that opens when the packet fits. A brief methods paper can describe the capture, the controls, the rotation and exposure checks, and the independent confirmations. The figures can be raw frames with measured points, not glamour shots. If reviewers can reproduce the paths and confirm that artifact routes were blocked, they will pass it along. If they find a hole, that is a gift you can close before the next window. Public culture shifts too. The comment that once said looks like a Sharpening scar now reads the rotation test and quiets down. The claim that once hung on a single screenshot now walks with a sequence. The burden moves from believers to skeptics. To knock the triangle down, a critic must show a specific failure in timing, in rotation checks, or in cross-site agreement. Friendly fire from careful skeptics becomes an asset because each resolved objection thickens the rope. If the signal survives and repeats, targeted campaigns follow. Coordinated imaging runs track the same region across longitudes to catch continuous motion. Photometry teams look for small, repeating brightness changes that would reveal spin. Polarimetry experts consider whether any reflection features appear that common dust cannot mimic. Particle missions like Parker get a calendar ping to check their logs near those times for any oddities in the solar wind. Each pillar is modest alone. Together they build something that decides history. Could this all be a cosmic coincidence? A rare surface structure pretending to be geometry? It could. That is why the first branch in the logic tree matters so much. If it rides rotation, it is the sun teaching us a new trick. If it does not, the conversation changes from clever plasma to technology. We keep both doors open until the numbers slam one shut. If the triangle holds, the ending is not an ending, it is a beginning. A repeatable, plain language protocol enters the world. Anyone can run it when the next anomaly appears. Institutions listen sooner, crowds record better. The distance between backyard and billion-dollar telescope shrinks. A small, dark shape near a star will have forced us to become a sharper species. That would be a worthy discovery even before we learn what the triangle is. Picture the next clear morning. Clips roll in from Texas, Brazil, Spain, South Africa. The camera rotates and the sharp edge rotates with it. Exposure nudges up and the angle melts to mush. A second sight captures the same sunspot, group, at the same minute, and nothing geometric appears. The blind processing bake-off returns stacks without a triangle unless someone leans hard on sharpening. That is not defeat, that is diagnosis. The shape was living in glass, gain, and hope. When anomalies collapse under gentle pressure, they leave a map of how not to be fooled next time. We gain a catalogue of artifact fingerprints for Herschel wedges and filter trains, which adapter lengths invite internal reflections, which camera sensors paint repeating faint triangles at particular gains, how vignetting sculpts gradients into fake edges when contrast is pushed. A few hours of side-by-side testing can pin each gremlin to a cause, then pin a fix to each cause. Paint the inside of that tube. Flip that spacer. Cap that slider at a lower radius. Publish the recipes. Future observers save days by not stepping in the same holes. A fade also tightens the community culture. The highlight reel that once chased every crisp geometry learns to post companions. Near frames with nothing odd. Raw clips alongside stacks. Plots of seeing and wind. The pins at the top of threads shift from speculation to method. The glossary grows. Newcomers learn quickly that a prominent scope shows the wrong layer for photosphere edges, that a rotation test is automatic, that a single frame is never a claim. The mood cools without losing curiosity. That is a healthy evolution. Science wins even when the headline shrinks. 3I Atlas continues to be a rare interstellar comet with a close past that stressed its ices and flung a tail through a brutal environment. Polarization curves and spectra keep arriving after conjunction and sharpen models. Maybe its dust is a bit shinier than average. Maybe its water to carbon monoxide ratio nudges the edge of our familiar clusters. Those are real, publishable results that tell us what other planetary nurseries might make. The mystery trades shape for chemistry, drama for detail. That is not lesser, it is deeper. Debunking teaches motion literacy. By tracking the non-appearance of a geometry across sequences and longitudes, volunteers develop muscle memory for solar rotation rates at different latitudes, for how sunspot motes sculpt light, for how granulation dances when the air is steady versus boiling. Those instincts will help catch the next real oddity faster because people will know what everyday weirdness looks like and will stop flagging it. Media literacy levels up too. Viewers who rode the roller coaster learn to crave receipts rather than vibes. A viral screenshot without raw files begins to feel thin. Channels that publish negative results alongside hot claims earn durable trust. The dopamine hit of maybe gives way to the satisfaction of measurable. That shift is contagious. It spills into other stories far from astronomy and pays dividends in every field where images can fool us. There is a practical payoff inside the null. pipelines get faster. File name templates that embed time, focal length, and filters become standard. A shared repository emerges where raw solar clips live, with checksums and README files, so strangers can verify nothing changed. Small tools appear as script that plots the drift of a feature against expected rotation, a widget that overlays a solar longitude grid, a button in processing software that runs an automatic rotation test and warns if an edge spins with the sensor. We did not get an artifact from the sun, but we built artifacts that make good practice easy. Professionals benefit too. A cleaned-up community reduces noise in their inboxes and improves the quality of tips worth chasing. A well-documented false alarm can be as valuable to a mission as a hit because it sketches the boundary conditions where instruments are likely to be fooled. When amateurs send a packet next time, it will already look like a methods section that earns attention even before the image loads. Most importantly, the emotional compass gets recalibrated. The thrill of a chase does not hinge on a single outcome. If the triangle fades, we keep the muscle that matters suspense braided with restraint, curiosity that loves tests more than headlines. The story we tell about ourselves changes from we almost found aliens to we found the line between artifacts and reality, and we learned to walk it better. That is a story worth sharing. Could this all be a cosmic coincidence? A dozen small factors lining up to draw a perfect edge that never belonged to the Sunday yes, and proving that is progress. Each gentle failure shaves a layer off our collective gullibility. Each careful null makes the next yes louder when it finally arrives. When 3i Atlas reappears from the glare, dimmer and farther, our instruments and our instincts will be sharper. If something real crosses our frame then, we will not need a legend. We will have a ledger. This is where the audience becomes a lab, not a comment section, a network. You do not need a telescope to help. You need a plan, a clock, and a way to package truth so strangers can check it. The mystery lives or dies on shared work done well. Here is how we do it together, without burning eyes or gear, and without drowning in chaos. First, safety is the line we never cross. Never point any optic at the sun unless it is built for solar work. Use front-mounted solar film or glass for full disk views. Use a Herschel wedge only on compatible refractors. Cap the scope when you step away. If you do not know your hardware, stop. Curiosity without caution turns into damage. We will repeat these rules until they are boring. Boring is good. Second, time is our common language. Set your phone to network time and treat those seconds as sacred. When you capture or download anything, write down the start time and end time in hours, minutes, seconds, and world time. Accuracy beats swagger. 2 clips taken a continent apart can become one continuous record if the clocks agree. If you have a telescope, your job is disciplined capture. Pick a target sunspot group from a fresh full-disk image. Record short clips in sets with a steady cadence. Keep exposure sane so highlights do not clip. Rotate the camera once during the set. Bracket brightness a little. Save the raw files. Then write a 1-page note with location, instrument, focal length, filter stack, exposure, gain, sensor temperature, seeing, and wind. That note is your passport. With it, another person can reconstruct your night and try to break your claim. If you do not have a telescope, you are still vital. Become our archive team. Pull the public frames from the Solar Dynamics Observatory that match the times of each claim. Grab the minute before and the minute after. Save the sequence as a short stack and mark the region where the triangle was reported. If the shape is on the surface, the archive will show it rolling with rotation. If the archive is clean, log that too. Negative results are not empty. They are boundary lines. We also need weather scribes. When you are near an observer, note clouds, wind, haze, and heat shimmer during their window. Post those in a single comment with timestamps. Seeing can make or break a shape. A triangle that appears only during boiling air is a warning. A triangle that holds through steady seeing is more serious. Naming sounds trivial. It is not. A clear name makes files travel farther. Use a simple pattern built from date, time, place, instrument, and exposure. Think of a tag that reads like this: year-month-day-hour minute second-city-scope-filter-exposure. Keep it short enough to read, long enough to carry meaning. Add a small text file with the same information inside the folder. If the file wanders the internet, the facts travel with it. Processing should be a duet. One person who believes a feature is there, one person who does not. Both use conservative settings first, light sharpening only, modest contrast. If both recover the same edge at the same spot, in the raw, the signal gains weight. If only one can conjure it with heavy hand sliders, call it art and move on. We will celebrate beautiful art. We will not mistake it for the sky. Reporting needs a front door. We will maintain a single page where you can drop raw clips, quick look stacks, and the one-page method note. Each entry gets a short status. Candidate, refuted, inconclusive. Do not chase labels on social feeds. Check the page. Update the state when new tests land. The goal is a ledger, not a rumor mill. Coordination keeps coverage continuous. Use world time and a simple grid on the solar disk to divide shifts. Morning crews in one hemisphere, hand off to afternoon crews in another. If a region is undersampled, we will post a gap alert. If a window is oversampled, we will shift eyes elsewhere. This is not herding cats. This is a relay. Teachers and translators, you are part of the team. Turn dense posts into clean explainers that a 12-year-old can follow. Make short clips that show a rotation test in action. Convert jargon into plain speech without dumbing it down. When knowledge flows, quality rises. Most of all, protect the culture. Praise the person who changes their mind in public. Pin the post that debunks a popular error with grace. Treat a clean null like a trophy. Curiosity plus discipline will beat hype 10 times out of 10. That is how a crowd becomes a method. Here is your invitation. Pick a lane and join. Image with care. Search the archives. Log the weather. Name files so strangers can trust them. Push your favorite claim through gentle pressure and see what survives. When the object returns from the glare, the network will already be humming. If a real triangle crosses a sunspot, then we will not need to argue. We will have the footage, the notes, and the receipts. Wonder is the spark. Skepticism is the steering wheel. Lose either, and you end up stuck or in a ditch. Our story has lived at that. Intersection from the first frame. A crisp, dark triangle near a sunspot lights up the imagination. A community builds a test plan in real time. Then the quiet work begins. Rotation checks, exposure brackets, cross-site attempts. The thrill is not the claim. The thrill is the moment a result survives pressure or gracefully breaks under it. Humans are pattern seekers. That gift gave us mathematics and engines and the ability to read the sky. It also gives us faces in clouds and canals on Mars. The brain wants closure. When facts lag, it supplies endings that fit our priors. Confirmation bias whispers keep the hits and forget the misses. The Texas sharpshooter fallacy whispers draw the target after the bullets land. Pareidolia whispers call that triangle a craft and hurry. None of these are moral failings. They are default settings. Science is the manual that teaches us how to switch them off long enough to see what is there. This is why Tiago saying, "Chris, you won," matters more than the pixels. It models a habit that scales. Change your method when a better method appears. Update your belief when data moves. Admit a miss without losing face. That posture is not weakness, it is courage. The same courage underwrites a clean debunk. Saying we looked and it was an artifact is not a retreat. It is stewardship of attention, so the next real anomaly gets a fair hearing. There is a rhythm worth holding on to. Begin with curiosity. Frame a test that could prove you wrong. Run it with restraint. Publish the raw material that lets strangers check you. If the signal fades, thank the test and bank the lesson. If the signal holds, tighten the claim and invite sharper knives. Every step leaves receipts. Receipts survive when gossip dies. Skepticism is not cynicism. Cynicism says nothing is real and nothing will change. Skepticism says, show me how you know, and I will walk with you if the path is clear. It is even more generous than belief, because it promises attention whenever the repost. Work is honest. A skeptic is the best ally a discovery can have. When the skeptic nods, the world follows. Wonder is not gullibility, it is readiness. It keeps us awake to the possibility that the universe can surprise us on a random weekday. It kept Galileo at the eyepiece when the moons of Jupiter refused to vanish. It kept a graduate student staring at a noisy plot until pulsars were born. It keeps a backyard observer willing to point into glare and try a different filter, even after a string of failures. Wonder fuels the repetition that skepticism demands. There is a simple code we can carry into every mystery that comes next. Love methods more than conclusions. Love predictions more than post hoc stories. Love null results that clarify the map as much as hits that redraw it. None of that will trend for long. All of it will last. When you feel the tug to finish the story before the data arrives, ask 3 quick questions. What result would make me change my mind? What outcome would count as a fail by my own rules? What evidence would convince my sharpest friendly critic? If you cannot answer, slow down. If you can, write those answers down before you look. That small act turns a hunch into a hypothesis. The triangle will choose a lane soon enough. Surface geometry that teaches us new solar physics. A repeatable free mover that invites technology into the conversation. Or an artifact that trains a generation of observers to stop seeing what they want and start seeing what is. Any branch is a win if we walk it with discipline and keep the receipts where others can read them. So what kind of species do we want to be when the next anomaly draws itself on a sensor? The kind that leaps to the wildest ending and digs in? Or the kind that leans forward with bright eyes and steady hands and says, "Let us test that"? The answer will echo past this video and this object. It will shape how we meet every claim from here on. Keep your wonder. Sharpen your doubt. The line between them is where discovery lives. After the glare comes the quiet. Then, a pale ember rises from the sun's neighborhood and slides back into a sky we can measure. 3i Atlas returns from conjunction dimmer, colder, and farther than when this story began, but not gone. The universe gives us a second pass. If we have learned anything, it is how to use it. Here is the plan. The moment elongation opens to a workable angle, we restart the relay. Morning cruise in the east, afternoon cruise in the west. We split the solar disk into a simple grid and assign lanes. We post a live schedule that shows who is watching which region and when. If a gap appears, a ping goes out and another scope steps in. The rules stand: short clips, conservative exposure. Camera rotation once per set, brightness brackets, logs that include time to the second, location, gear, filters, and seeing. A one-page note travels with every file. We begin with baselines. Pull polarization points at multiple colors as phase angle changes. Build the curve slowly and cleanly. If it hugs the comet family, note it. If it peels away, raise a flag and call for more eyes. Run spectrographs when the object is bright enough to trust the lines. Check water, carbon monoxide, and the simple organics we expect. Watch for ratios that shift smoothly with distance rather than jittering with emotion. If numbers surprise you, celebrate and repeat before you announce. Astrometry teams go to work on the path. Short exposures. Tight timing. Modern star catalogues for calibration. Fit the gravity-only arc and publish residuals with honest errors. If a push appears, ask whether outgassing explains it before you ask for sails and thrusters. If outgassing fails, say so and show how. Meanwhile, the image crew watches the photosphere near the object's apparent position when geometry allows. If a geometry appears again, clean edges, persistent motion, coherent behavior, it walks through the replication plan on day 1. 2. Sights. Rotation checks. Exposure brackets. Blind processing. Publish raw within hours. Public archives are our time machine. We will mirror the frames from the Solar Dynamics Observatory and keep a simple index so a student with a laptop can rewind to the minute of any claim and check the sun itself. If a surface-linked triangle is real, the archive will remember it. If nothing is there, that narrows the field without argument. We will keep a second mirror for ground-based solar observatories where public data allows. If professionals give a yes or a no, we will pin it and treat it as a milestone rather than a verdict. Missions in flight might cross our path by luck. Parker Solar Probe will make more close passes. If our campaign's timeline overlaps, we will post coordinated windows so particle teams can tag their logs. The European Space Agency's Hera mission could sample dust fields in the inner system. If its instruments sniff anything odd near our windows, we will amplify that note for analysts who speak that dialect. None of these side channels will decide the triangle. They can tip attention in the right direction at the right time. Our infrastructure is ready. A single page lists active candidates with traffic light states. Green means independently replicated with raw available. Yellow means intriguing but incomplete. Red means refuted with method notes. Each entry links to a folder where raw clips, quick look stacks, and one-page capture notes live with checksums. A second tab lists null days for specific regions, so we do not waste effort rechecking empty hours. A small toolkit lives alongside a script for plotting drift against solar rotation, a widget to overlay a longitude grid, a template that autofills file names from gear metadata. Now, the tone. We keep the promise we made in the first minutes of this film. We will not inflate a maybe into a myth, and we will not bury a solid anomaly because it is inconvenient. We will push every claim through, the same filter. If it survives, we will say so and invite sharper knives. If it fails, we will say so and bank the lesson. Either way, we publish receipts you can check without trusting us. That is how a channel earns a place in your brain's tight circle of reliable voices. What if the triangle returns? Then history shifts from speculative to empirical, and the world gets loud. We will present the replication packet, the motion plots, the glint or thermal tests, if any, and the archive checks that show whether the photosphere played a part. We will invite professional teams to swing instruments if they can and to tell us no if they must. We will aim the curiosity of millions at the coordinates and the clock, not at a rumor. What if it does not? Then the story lands on what we have already gained. A smarter global network of observers, a culture that prizes raw data, pre-committed tests, and clean nulls. Tools anyone can use to check a claim without a professor's budget. A set of chemical and polarimetric facts about an interstellar visitor that will color textbooks. A playbook we can run next time in half the hours. So here we are again at the edge where glare meets patience. The sun still hides more than it reveals. 3i Atlas still moves on a path that began around a star we will never see with naked eyes. And we, the crew that watched, argued, tested, and learned, are ready. Subscribe, set notifications, and share this investigation with the person who needs wonder mixed with proof. When the light eases and the numbers flow, we will meet you here with receipts, not rumors.